All right, ladies and gentlemen, this is the video on manipulating K. This is going to be a fairly quick video. There's not a ton that goes along with this. This is a final topic of equilibrium, so it's not a major understanding that you have to have, but it does occasionally come up. So manipulating K is essentially calling back to the types of problems we did with thermochemistry with Hess's law, where when you flipped a reaction around, you flipped the sign on the delta H value. If you doubled the coefficients of the reaction, you doubled the value for delta H. That's sort of what we're talking about when we say manipulating K. However, the rules are different because of how K works. K is not a positive or a negative value, it's always positive. It's always a ratio of products to reactants, and since you can't have a negative amount of reactants, you cannot have a negative K value. K can either be large or small, but it can't be positive or negative. So this is sort of the idea behind when I say manipulating K. I'm talking about making those, when you make a change to your reaction, how does it affect the value for K? So this is truly very similar to the delta H stuff, we just have slightly different rules. So first of all, the first one that's different, if you flip a reaction around, you do not take the negative, you do not flip the sign on K. There is no sign on K. K is either large or small. So if you flip it around, what you do is take the inverse of your K. You do 1 over K. Because K is products over reactants. If you flip your reaction around, it's now reactants over products. So you have taken the inverse. So we cannot sort of take the negative value, but we can invert the value for K, do 1 over K. If you are doing something to manipulate your reaction, you realize you need to multiply your coefficients by something, like double them or triple them or cut them in half. You're not going to multiply K by that value. Instead, you're going to raise K to that power. The reason is that you need to think about, where do coefficients affect K? How do coefficients come into writing our K expressions? And coefficients affect our K expressions because coefficients become the exponent, right? It's products over reactants raised to their coefficients. So coefficients are the exponent. So if you change the coefficient, you're changing the exponent on everything in that expression. So it's not a doubling or a tripling, it's a raising it to that power. You decide you need to multiply all your coefficients by 3, you have to cube your value for K. And then the last one is if you add your reactions together. Now in Hess's law, if we add our reactions together, we add our delta H values together. It's every change that you make to your reactions, you make the exact same change to your delta H values. Again, that's not the way that K works, because reactants are not added to one another in a K expression. It's not, reactants plus reactants on the bottom, or products plus products. It's products times products. It's reactants times reactants. So we have to multiply our K values together if we're adding reactions together. K does not work the same way as delta H does. So we cannot take the same set of rules. However, it is similar in terms of changes that are made to the reaction are sort of shown in how we write our K value. So we don't really exactly have sample problems for this, but I do just have some sort of things to show you what I'm talking about when I say flipping the reaction, multiplying coefficients, etc., etc. So if we take this reaction as an example, carbon solid plus oxygen gas goes to CO2 gas. We write an equilibrium expression for this reaction, right? It's products over reactants raised to their coefficients. We're going to omit the solid carbon because it's inappropriate to talk about its concentration. It doesn't really have one. So the K expression would look like this. And I am writing a Kc expression for this. You can absolutely write Kc. Basically, you can write Kc for any reaction at all. It's sort of your standard default go-to one. So this would look like the concentration of carbon dioxide over the concentration of oxygen gas, each raised to the first, because those are their coefficients. We're used to seeing that. If we reverse the reaction, we just flip it around. Becomes CO2 gas goes to C solid plus O2 gas, right? We've simply flipped the reaction. Now, if we're going to write a equilibrium expression for this reaction, it is going to be the exact inverse of that one that we wrote for the first reaction, right? It's going to be the concentration of oxygen gas over the concentration of carbon dioxide gas raised to the first. You have flipped your K value. So we're not flipping the sign. There is no sign for K. There's never a sign for K. It's always positive because it's always a ratio. It's just talking about how much product there is in relative to the amount of reactant that there is. If we flip our reaction around, we invert our K value. K is inverted. It's not negated. We don't negate K ever. You can't have a negative amount of product. You can't have a negative amount of reactant. It's always going to be positive. But we can flip the fraction, which is exactly what we're doing, right? We reverse the reaction, we flip our value for K. We would just do 1 over K, and that would be the new Kc value. If we take the exact same reaction, again, and write the equilibrium expression for it, carbon dioxide gas over the concentration of carbon dioxide over the concentration of the oxygen gas. If we were to take the same reaction then and double it so that the coefficients are now 2, we've got 2 carbon solids plus 2 oxygen gases goes to 2 carbon dioxide gases. If I asked you to write the equilibrium expression for this reaction now, what you're going to do is Kc is equal to the concentration of the carbon dioxide squared divided by the concentration of the oxygen gas squared, because coefficients become exponents in the K expression. So what's the difference between these two Kc values? We've taken that doubling and we've squared the K. The value for Kc is now squared in comparison with the original one. It is not doubled. You are not simply multiplying the K value by 2. That is not what's going on here. Coefficients become powers. They become exponents. So if you need to change your coefficients for your reaction, the change that you make for the K value is taking that value and then raising it to that whatever change you had to make. If you had to double it, if you had to cut it in half, if you had to triple it, etc., etc. So if we double our coefficients, we do not double our K value. We raise that K value to that new power because coefficients become the power in the K expression. So in general, if you are given a problem where you are asked to find a K value for a reaction, and maybe you're given other K values for other reactions. Essentially, think of it like as a Hess's law problem, where it says, like, hey, find the delta H value for this target reaction given these other reactions and these other delta H values. So sort of thinking about it that way. The first thing that you want to do is write out the reactions for the other K values. I mean, that's kind of important, right? If it gives you KSP or Ka or Kb, you want to sort of write those reactions down, because that's kind of a hint that you're going to be manipulating the reactions the exact same way that we used to manipulate the reactions with our delta H Hess's law stuff. And then like the next thing it says to do our Hess's law type manipulations to add the reactions together to get the target reactions. Essentially determine what is it that you need to do to these other reactions, to these KSP reactions, to these Ka, Kb, etc. reactions, so that you can add the reactions themselves together in order to get your target value, and then perform the appropriate calculations with K, meaning if you had to flip one of your reactions around, then you want to invert your K value. If you had to multiply one of your reactions by 2, then you have to square your K value, and then at the end, when you add them all together, you do not simply add your K values together. You multiply your K values together at the end. So that's the other sort of key difference that I didn't really go into, but if you're adding reactions together, you have to multiply your K values together. And that's actually where the Ka times Kb is equal to Kw. If you take a Ka reaction and you take a Kb reaction for the conjugate base and you add those reactions together, what you actually wind up getting is H plus OH minus, the autoionization of water. You will get that Kw reaction. So Ka times Kw, Ka times Kb gives you Kw. If you add Ka and Kb reactions together, you get the Kw reaction, and that's where that relationship comes from. So you do not add your K values together at the end, you multiply them. So those are the rules. They're slightly different rules. Like I said, this is quick. This is actually the end of the video. It's not a topic that comes up all that often, but we are going to have a brief problem set on it. It's going to be shorter than the others because, like I said, this is a final topic, and it's not one of the important final topics. Q and Le Chatelier are the important final topics, but we will be practicing a little bit with this in class.